All right, so the first thing I want to go over is the properties of the standard deviation. And here we have the question. It says the standard normal distribution has a mean of 0. This is just an example. And standard deviation, which is used the symbol sigma. Sigma equals 1. So sigma is always used for standard deviation. Is always used for standard deviation. And the Greek letter mu is always used for the mean. So this is the Greek letter mu. This is the Greek letter sigma. Mu and sigma. So if I'm looking at the 68, 95, 99.7 rule, this is kind of how it works. If I have a mean of 0, I know that 68% of the data lies within 1 standard deviation of the mean. So that means if I go 1 standard deviation this way, and since my standard deviation is 1, that's going to get me to -1. And if I go this way, it's going to get me to, I need to add a black tick there. That's going to get me to a +1. Then I know that between there and there is 68% of the data. So between -1 and 1 is 68% of the data. So 68% of the data lies between those two values. 95% of the data is within 2 standard deviations. So instead of just going 1, I'm going to have to go 1, 2 in each direction. So that means down to -2 and up to a +2. Between -2 and +2. And between those two values, I'm going to have 95% of my data. So that means 95% of the data in a normal distribution curve is between -2 or 2 standard distributions. And you can see that because, and that percentage stands for the area underneath the curve. The area underneath, so all this area underneath the curve is 95%. And then the last one, 99.7, almost all of the data is contained within 3 standard deviations. So 1, 2, 3, down here at -3, and up here at 1, 2, +3. So between there and there is 99.7% of the data. Okay? And you might see these kind of curves in like, this is used a lot for like birth weight and stuff like that. And that's kind of how it works. Like if you're in like the 90th percentile, that means you're way up at the top somewhere. And if you're at the 4th percentile, it means you're way down at the bottom. Like the bottom 4% or the top 90%. So between, between -3 and 3. Okay? So you look at where first of all, you start with your mean, you put your 0, then you look at what your sigma, your standard deviation is, and you move that many in each direction. All right. So, the next part. In addition to the probabilities areas for the 68, 95, 99 rule, you can also find the area using a graphing calculator. For this exercise, I'm going to use the tables because I'm not sure everybody has a graphing calculator, so I'll just use the tables. So, cross that out. I'm going to say using a table. The table gives you, and same thing, the table or calculator, doesn't matter, calculator or table, will give you the area always to the right, or to the left, sorry, always to the left, okay? You can use a graphing calculator for this, but I'm just going to show you how to use the tables, because it's just as easy. So, first thing, sketch a graph of the standard normal curve, shade in the area of interest, and use the table or calculator, so we're going to use the table to find the area. Okay? So we have determined each area under the standard normal curve to the left of 1.57, to the left of 1.57. So what I would do is I would have my curve. Okay. I would look at my table. This one doesn't actually show it. This one shows it pretty well. And the mean is always assumed at 0. At 0. And you have two tables. You have one that has negative values, and you have one that has positive values. These are for the z values. So if I look at the question again, it says to the left of 1.57. That's a positive value. So that means I'm going to have to be looking at my positive z table. And the positive z table, I'm going to have to look at 1.57. So here is 1.5. And then I look up at the top to get me my second decimal place, 7. So I go down where it matches up with the 1.5. 1.50, 1, 2, 3, 4, 5, 6, 7. So 0.9418. 0.9418. 0.9418. Okay, 0.9418. And how that would kind of look is, for my normal distribution curve, I would have 0 as the mean, and I would go up to 1.57. So there's 0. That would be 2. So there is 1.57. And what it gives me is the area to the left. So it's going to give me all the area to the left of the entire curve, underneath the entire curve. And that area represents 0.9418, or we could write that as 94.18% of all my data. So the Z table gives you the decimal. If you needed to convert it to a percent, you would just convert it to a percent. All right, the next one. To the right, oh, there's a different one now. To the right of negative 2.45. So again, I have my curve. Oops, let's draw that a bit better. My curve here. That's even worse. Oh well. And here is my 0. Negative 2.47 is going to be over here somewhere. And we want the area to the right this time. To the right. So we're going to have to do something a little bit different. Because the tables always give you the area to the left, this time we're looking at negative values, we want negative 2.47. So I look for negative 2.4 right there. And then I go over 0, 1, 2, 3, 4, 5, 6, 7, matched up with the 7 at the top. And I get 0.0068. But that is the area to the right. Or sorry, that is the area to the left of the curve. So that would be like the area over here, but I don't want that area, I want this area. You have to know for this one that the total area underneath the entire curve is the total probability, which is 1. Which is 1. So the total probability is equal to 1. We have to subtract off the area that's over here, which it gives us, which was 0.0068. So 1 minus 0.0068. 1 minus 0.0068, which is equal to 0.9932. So that means the area here is 0.9932, or 99.32%. Okay? So when you're dealing with to the right, you're going to have to take the total, which is 1, and subtract off the area for which you found in your Z tables. Okay? Start off with 1, subtract off the area that you found on the Z tables because we're looking to the right. Next one, between. Okay, now this is even different. So here's my curve, my 0, and I want between negative 1 and positive 1. Negative 1 and positive 1. I want just the area between here. The way to find that, again, the Z tables always give you the area to the right, So if I take the area to the right of 1, I'm going to get all the area there. If I take the area to the right, sorry, to the left, to the left. If you take the area to the left of 1, you get all the area over there. If you could take the area to the left of negative 1, you get all the area to the left of negative 1. I want just the area in between. So what I have to do is I have to take the top one, all that area, subtract off the bottom area, and then I'll be left with just what's in between. So take the top minus the bottom. Top minus bottom. Okay, but we still have to use our Z tables to figure this out. So, first thing I look at is 1, the area for 1, positive 1. Oh, so I'm looking at my positive table. 1 Now I'm not going to be going over any because I just want 1.0, which is 0.8413. Whoops. So I get 0.8143 minus the bottom area, which is negative 1. So I go to negative 1 and just do the first one over, which is 0.1587. 0.1587. I subtract the two, so I get 0.8143 minus 0.1587. I get an area of 0.6556. 6556, which is equal to 65.56%. Okay, so 65.56% of the data lies between -1 and +1. Okay, and that's just using the Z tables and subtracting off the top minus the bottom. Same thing, so I have between -1.3 and 2.1. So again, I take the top minus the bottom, and the top value is 2.1, so I'm going to have to look at my positive Z table, 2.1, and it's just 2.1, so it's going to be 0.9821. So 0.9821. The bottom is -1.3. -1.3, and again, it's just the first one, I'm not going over any, is 0.0968. 0.0968. I subtract the two, so I get 0.9821 minus 0.0968, and I get an area of 0.8853. So I get 0.8853. I didn't sketch this one this time because I'm just dealing with the, just the areas. So 88.53% of the data would lay between -1.3 and 2.1. Okay, -1 in the same method of right above there. Same thing. Last one, between 1.5 and 2.5, or 2.5, so top minus bottom again. So the top is 2.5. Look at my positive Z table, so I get 2.5 is 0.9938. So 0.9938. Subtract off the 1.5, that's a positive value again, so I go 1.5, 0.9332. Okay, and that one is going to be equal to 9938 minus 9932. Whoops. 0.9938 minus 0.9332 is 0.0606. So 0.0606, or that's equal to 6.06%. Okay, so it's a good idea to think in terms of your decimals and your percents. Like right here, it says what percent of the standard normal population is between -1.5 and 2.5. We've done those, and that's just converting it to a percent afterwards. If it asks for, what are these ones? These ones ask for determine the area under the standard normal curve. So the area is the first number. Area is the first number. So the 0.9418, the 0.99, the 0.66, this one here, that's the area underneath the curve. The percent, if it asks for a percent, you need to convert it to a percent. So this question is exactly the same as the ones that we just did above. So we got -1.5, so we're looking on a negative table. -1.5 is 0.0668. Oh, we just did that one, right? So the one above, the percent is going to be 6.06%. So if it asks for the percent, convert the area to a decimal. Convert the area to a decimal. And remember that convert the area to a percent. And remember that the area underneath the curve, the total area is always equal to 1, because the total percent is 1. 100%, which is equal to 1. All right. But what if we aren't given the data in terms of the Z score? Right? What if we aren't given that? We can convert any set into z-scores by using this formula here. Z equals x minus mu over sigma. X is your given value, mu is your mean, and sigma is your standard deviation to get your z-score. Why is that important? Because once you have your z-score, you can just look on the tables, right? Once I have my z-score, I just look at my value of a z-score and I look over here to figure out what percent or what area I'm dealing with, right? So the first one says, for the population of adult sockeye salmon, suppose that the lengths of the salmon are approximately normally distributed with a mean of 78 and a standard deviation of 8. So my mu is equal to 78 and my sigma is equal to 8. It says, sketch a normal curve to show the distribution of the lengths of the sockeye salmon. Then it says, mark the values on the horizontal axis that are 1, 2, and 3 standard deviations from the mean. Alright, so here we have the mean of 78. That's right in the center. Your mean is always in the center. And then if I go 1 standard deviation to the left and right, that's 8, a value of 8. So that means if I go over here, that's going to be 70. If I go up here, that's going to be 86, because I'm going up a value of 8 for every 1 standard deviation. If I go up again, so that's the value for 1. If I go up again, 1 more, then that means I'm going 8 again each direction. So this is going to be 62, and this is going to be 94. So that's 2 standard deviations. So first thing I did is I went 1 sigma, then I went 2 sigmas. Now what it wants me to do is 3 sigmas. So I'm going to go 1 more. Right there and right there. So I go 1 more, 8 up. Every time I'm going 8 up. So I get 102. And if I go down this way, it's going to be 54. Okay? And that's going up 3 sigmas. And that's going down 1 sigma. Right? 2 sigmas and 3 sigmas. Now remember your rule, the 60, remember what was it again? Let's just double check here. 68, 95, 99. 68, 95, whoops, 99. So that means that between here and here, between 1 standard deviation, all in here, okay, is 68% of my data. 68% of my data lies within 1 standard deviation. So that means if I'm going half that, so if I'm just going to take half that into consideration, oops, that means that only part of it is going to be 34%. And 34%. It shows this in your textbook as well. The whole thing is 68, therefore each part is 34. So this question says, what is the probability that a randomly selected adult sockeye is between 72 and 80? I don't have 72 or 80, but I can add them in, right? I can add them in. I know halfway between 70 and 78 is right there, and it's going to be 74. Halfway between 70 and 74 is going to be 72. So if I need to kind of redraw this normal curve, which I'm going to do, right? I have my value of 78. I'm going to put in my value of, I'm going to expand this a bit, 72. It's a terrible curve. I'm going to redo that. So I have over there, goes up, and then down, and then over like that. So 72. And what's the percent between those two? Well, if I cut the 34 in half, that would be my 74. 34 divided by 2, 34 divided by 2 is 17. So that means each section would be 17 and 17. And then if I cut it in half again, I'm going to take 17 divided by 2. So I get 8.5. So 8.5% is between 72 and 78. And that's a jump of 2. So if I go another jump of 2, it'll get me to 80. And that's going to be another 8.5%. So I have 8.5 plus 8.5 is equal to 17% of my data, which is the probability that it will be between 72 and 80. So it's just a matter of taking, you know it's 68%, that means each section is 34. If I cut that in half, it's 17. If I cut it in half again, it's 8.5. That means every jump of 2, and I could figure out for every jump of 1, so that if this said anything, I could say, okay, well, there's however many between those, so it'd be easy to figure out, right? All right. We can also, though, instead of cutting the graph in half, which is kind of difficult, we can also use z-scores to compare two similar sets of data. Z-scores work on the formula z equals x, which is your given value, minus mu, your mean, divided by sigma, which is your standard deviation. It says, Marion is a sales representative. Her total sales for the last year and this year were 1.725 million and 1.65 million, respectively. So that means your total sales for last year were 1.725, this year 1.65. It says last year her mean sales were, for the company, were about 1.6 million, with a standard deviation of 0.2 last year. So the information for last year is going to be kept separate for the information from this year. Okay? We'll do them in two different colors. I'll use red for last year, and I will use green for this year. So, last year, and we're trying to figure out what the z values are. So for last year, my z value is going to be equal to, x is my given value. That's her total sale. That's this value right here. Last year, her total sales were 1.725 million. I have to subtract off the mean for last year, which is, it says the mean sales for the company were 1.6. Divided by the standard deviation for last year, which was 0.2. And this will give me my z value for last year. Okay, so I bring up the calculator, I go 1.725 minus 1.6 is equal to 0.125. Divide that by 0.2, I get 0.625. So 0.625 is my z value. Remember, that's my z value, not my probability. In order to find my probability, I go onto my z table. It's a positive value. Whoops. Positive 0.625. So we're dealing with 0.6. And we don't have 25, but we'll use 2. It's in between 0.7324 and 0.7357. So 0.7324 and 0.7357. It's right in between the middle of those. How would I figure out what the middle of that would be? Well, I could just subtract the 2 and figure out how much is between them. So I would say, okay, 0.0625. So it's 0.7324 and 0.7357 minus 0.7324. Subtract the 2. I know there's a difference of 0.0033 between the two. So that means I would divide that by 2. And I want to go 0.00165 up from my 0.7324. 0.7324, I add it, and I get approximately 0.73405. 0.73405, and that's my probability, which is equal to 73.4, we'll round that off, 73.4%. So if you had just used, I don't know, 0.62, or rounded it to 0.63 and gotten 73.6%, you'd be pretty close. 73.4, 73.6 is all right. All right, so this year, my values are a little bit different. My z is going to equal, this time I'm using the 1.65 million, because that was her total sales. Everything else stays the same. No, it doesn't. Sorry. The mean for this year was 1.53. the standard deviation for this year was 0.15. Okay, so totally different values for this year, which makes sense because your mean sales, your average sales are going to be different, and the amount that it deviates from the mean is going to be different as well. So same thing, I just go in the calculator, I go 1.65 minus my 1.53, I divide that by my 0.15, I get a z value much easier of 0.8. So my z value equals 0.8. I go on my z table, I find 0.8 is 0.7881, 0.7881. Okay, and that's her z value, that's her probability, which is 78.81%. So it says, in which year did Marion perform better relative to her colleagues? In this question, we want the higher number because we want her sales to be bigger, more percents of sales, right? In this case. If it said, like if it was a question about time or something, or which time, then you want a lower time, right? So you want the lower number. But in this case, because there's a question in the book like that. But in this case, because you want her total sales, she did better this year. Okay, relative to her other colleagues. She had 78.81% of the sales. Even though you look at the numbers to start with 1.725 and 1.65, it would look like she did better last year. But because of all the different numbers, because of the mean was different last year and the standard deviation, right? This year, the mean was much lower. So definitely everybody's sales are going to be lower. And the standard deviation is also lower. So that means there's less error, less standard deviation. So that's the end of part 1. I'll finish the end of part 2 next.